All right, welcome back. Let's take a look at the tentative schedule. We're sticking a schedule, all right? So today is the end of August. Don't forget to pay your rent and stuff, all right? August 31st, finishing lesson 9 and doing lesson 10, which means that we're finishing the material for the first part of the course, lessons 1 through 10. That constitutes the first homework assignment, okay? So what's going to happen is we're going to finish discussing the material today, all right? Oh, I gotta mute people, by the way. All right. So we're finishing the lecture material today. On Wednesday, that'll be an open forum, primarily for student questions, like how to work out things on the homework, probably. All right. Next Monday is a holiday where we can all take a nice, well-deserved rest, and also, wrap up some loose ends. And then Wednesday of next week, September 9th, I'll quickly go over the answers, but you really have to know your stuff in order to keep up, okay? Make sure you're prepared by that Wednesday the 9th. And then the actual homework for these first 10 lessons, we do the next day, by the end of the day, September 10th, Thursday. All right, that's the game plan. No changes. Any questions about that? Any questions about that? Okay. So let's go ahead and start. We're going to finish about 9:40 today, by the way. All right.
Hi, everyone. We're continuing with lesson 9 on measures of variation. Now, thus far, we've discussed how to compute a population standard deviation and a population variance based on population data, and also a sample standard deviation and sample variance based on sample data. The purpose here being to estimate the values of sigma and sigma squared up in the population. We ultimately care about the values of these population parameters. But let's say that we know, or that we estimate, that the population standard deviation of a data set is, let's say, 10 points, like on an exam. Well, so what? So what that the population standard deviation is 10 points on an exam? What does that mean? How do we apply these ideas? Applications of SD, standard deviation. How can we use a population standard deviation or a sample standard deviation, assuming that it does in fact do a decent job of estimating the population standard deviation? Well, the easy answer to this is that we can compare the variation between two different populations. So for example, if we have a population of men and a population of women, then we can compare the standard deviation for the men with the standard deviation for the women. And maybe one group exhibits greater spread. Or if you consider two different classes, maybe an evening class and a morning class. Maybe the evening class has a very high standard deviation, a lot of spread in the scores, but the morning class has a small standard deviation, not so much spread among the scores. So if Professor Dumb's evening class has a much higher SD on a standardized test than Professor D's morning class does, then that could reflect a greater variety in the students in Professor Dumb's class. By the way, this is a takeoff on Tweedledum and Tweedledee, these guys. These two characters from Alice in Wonderland by Lewis Carroll. Hey, that copyright stuff's expired, so I can use it. All right, so aside from comparing populations, well, let's say that we just have one population. So the standard deviation is 10 points. So what? Well, the standard deviation can help us find how close to the mean. Remember, the mean was a key parameter that we planted our flag at. We can use the standard deviation to find how close to the mean we expect most of the population values to be. So based on the standard deviation, how spread out about the mean would we expect the values to be? And in number 3, in particular, can we find an interval of usual values for the population? So given a mean and a standard deviation, what would be a usual or typical value versus what would be unusual? So now we will talk further about applications of standard deviation next time.
All right. Any questions thus far? Questions thus far? All right, looking at applications of standard deviation.
Hi, everyone. Chebyshev's theorem and the 68, 95, 99.7% empirical rule help us understand how population values are clustered about the mean. Remember, the mean is an important flagpole that we plant in the data. And let's say that one standard deviation, sigma, is like a yardstick. It's like a basis for measurement. The idea is that we can't have too many values too far away from the mean. Both of these rules imply this. So this is one standard deviation. We cannot have large chunks of data that are too far away from the mean in terms of standard deviation. So for example, we can't have too much of the data that's more than 3 or 4 standard deviations away from the mean. So there has to be a certain clustering about the mean. It doesn't have to be close in like this, but you can't have huge proportions of clumps way out here and way out here. Now, a difference between these two rules is that Chebyshev's theorem applies to any distribution shape with finite standard deviation. So it applies to not just a bell curve, but also to something like this, or something like this, or something like this. Any sort of messed up shape, as long as you have finite standard deviation. And I'm not going to mess with you on infinite standard deviation in this class. So because Chebyshev's theorem applies to really any distribution shape, we say that it is by definition robust or distribution free. Now, what does this theorem say? Well, regardless of the distribution shape, at least 3/4 or at least 75% of the population values must lie within 2 standard deviations of the mean. So again, our flagpole is at the mean, mu. Here's 2 standard deviations above the mean, mu plus 2 sigma. I'll write it in red, mu plus 2 sigma. And here's 2 standard deviations below the mean, mu minus 2 sigma. At least 3/4 or 75% of the data will have to lie between these two goalposts. So it could be 75%, could be 80%. It could be actually all the data. That is possible, or all the population values. But it's guaranteed that at least 75% must lie within 2 standard deviations of the mean, which means that at most 25% can lie more than 2 standard deviations above the mean. At most 25% of the population values can lie more than 2 standard deviations away from the population mean. I'm assuming for now that we're dealing with population data. So again, we can't have too much too far out. We cannot have more than 1/4 or 25% of the data values or population values more than 2 standard deviations away from the mean. Again, the idea is that one standard deviation is like a yardstick or a basis for measurement. It could be 10 points on an exam. It could be 5 pounds when it comes to weights. It could be 42 light years in astronomy. Whatever one standard deviation is. Okay, so at least 3/4 or 75% of the population values have to lie within 2 standard deviations. Well, more than that, at least 8/9 or at least 89% of the population values must lie within 3 standard deviations of the mean. So again, here's our flagpole at the mean. So within 3 standard deviations of the mean, that means we're going from mu minus 3 sigma to mu plus 3 sigma. At least 89% of the population values must lie in here. It could be 89%, could be 95%, could be 99%, could be all the values. In fact, it wouldn't be shocking at all if all the values were within 3 standard deviations of the mean. And that means that at most 11% of the values can be more than 3 standard deviations away from the mean. Again, let's assume we're talking about population data, population standard deviation, population mean. So again, we can't have too much too far out. You can't have high proportions of data that are 4 or 5 standard deviations away from the mean. So that's Chebyshev's theorem, which applies to a variety of possible shapes. Next, we're going to talk about the 68, 95, 99.7% empirical rule, which applies to bell-shaped distributions specifically, or approximately bell-shaped or normal-shaped distributions. That's next time.
All right, any questions? We're looking at what the standard deviation tells us about the distribution. Any questions? Any questions? Wait, 5.5, where's the 5.5%? Where's that from? Oh, well, it could be, but again, we're saying at most 11%. I mean, maybe all the data is within 3 standard deviations. We're saying that at most 11% can be outside. It doesn't have to be symmetric. It does not have to be symmetric. It could be, you could have everything inside here, in fact. Okay. I guess theoretically, you could have 11% past three standard deviations above, but that's kind of rare. Any other questions?
Well, shapes, shaped or normal shaped distributions. That's next time. Hi, everyone. Before we start with the empirical rule, let's remember that Chebyshev's theorem said that at least 89% of the data values had to lie within 2 standard deviations of the mean, and that at least 89% of the data values had to lie within 3 standard deviations of the mean. In fact, all 100% of the data values could lie within 2 or 3 standard deviations of the mean. The 75% and the 89% were lower bounds. They weren't estimates. They were lower bounds. It could have been 100%. But now, for more precise results, we can go to the 68, 95, 99.7% empirical rule. Empirical means something that we see from observation. And in practice, we often see these bell-shaped distributions. Normal distributions are the most famous type of bell-shaped distributions. We'll talk a lot about those in this class. But when you look at this empirical rule here, notice that we have precise percents, but there's a price that we pay. We get more precise results, but we need an important assumption or condition, namely the assumption that we have an approximately bell-shaped distribution. If you have a distribution shape like that, or like that, or like that, then you cannot apply this rule. So we do get more precise results here, but we have a key condition that not all distributions satisfy. This rule is not robust. It's not distribution-free. But if we do have an approximately normal distribution, something like a bell shape like this, then what the empirical rule says is that about 68% of the data values will lie within 1 standard deviation of the mean. Chebyshev's theorem didn't say anything about data values within 1 standard deviation of the mean. The empirical rule does. The empirical rule also says that about 95% of the data values will lie within 2 standard deviations of the mean, and about 99.7% of the data values will lie within 3 standard deviations of the mean. Now, these are consistent with what Chebyshev's theorem said, because what Chebyshev said was that at least 75% of the data values would be within 2 standard deviations. The empirical rule says for this kind of bell shape, about 95% will lie within 2 standard deviations. And Chebyshev said that over here, at least 89% of the data values would lie within 3 standard deviations of the mean. The empirical rule says more precisely about 99.7%, basically everything, if you have an approximately bell shape. Now, what's a way of visualizing standard deviations when we have something that's about normally distributed, where we have about a bell shape like this? So those of you who have studied calculus may remember the idea of inflection points. These are points on the curve where the curve changes from concave up to concave down, or vice versa. So this would be a piece of curve that was concave up. Here's a piece of curve that's concave down. It's like curving up versus curving down. So over here, on this bell shape, the graph is concave up, CU over here. It's concave down in the middle here, and goes back to concave up over on the right tail. The inflection points are the points here where the graph changes concavity. We also assume continuity, but that's a given. So the inflection points, the IPs, are where the curve changes concavity. Again, if you've taken calculus, these ideas may be familiar to you. If you haven't, don't worry about it. You don't need to know about inflection points in this class. But it is helpful if you want to get some sort of geometric sense as to what one standard deviation is, if you have a roughly normal distribution. So, what is one standard deviation? Again, think of this flag here at the mean, this flagpole at the mean. The mean line is the vertical line through the maximum point of this bell curve. Now, if we draw vertical lines through the two inflection points over here and over here, then one standard deviation, 1 sigma, will be the horizontal distance between the mean line and either inflection point. That's by symmetry. If you have one standard deviation from the mean line to this inflection point to the right, then you have one standard deviation, 1 sigma, between the mean line and this inflection point to the left. Okay, so one standard deviation visually is the horizontal distance between the mean line and either inflection point. You don't have to know that, but it's nice to know if you want to draw pictures that are accurate with bell curves, normal curves. So once again, the empirical rule says that with approximately normal data, about 68% will lie within one standard deviation of the mean, about 95% will lie within 2 standard deviations of the mean, and about 99.7%, almost all the data, will lie within 3 standard deviations of the mean. Now, these are not lower bounds. These are estimates. These are actual approximations. So if you have about normal data, then about 68% will lie within 1 standard deviation. It should not be the case that all the data, 100%, should lie within it. Chebyshev might say something like that, but no, the empirical rule gives approximate percents if you have about normal shaped data. And again, it's sometimes called the empirical rule. The 68, 95, 99.7% rule is sometimes called the empirical rule because approximately normal distributions are often seen in practice. And empirical means something that we see from observation. Next up, let's look at an example.
All right, any questions before we go to our example? Any questions? Let's go to our example.
Hi, everyone. Let's do an example of Chebyshev's theorem and the 68, 95, 99.7% empirical rule. So let's say that I'm teaching a large lecture hall class of 1,000 students, and all 1,000 scores on a test have been determined. And I find that based on an Excel spreadsheet, I find that the population mean for the 1,000 test scores is 50 points. And the population standard deviation sigma is 10 points. Excel can spit these out for me. Now let's say that the scores between 40 points and 60 points are the C scores on the exam. So I tell the students that if you score between 40 points and 60 points on the exam, then you're getting a C. And only those students are getting a C on that exam. Well, about what proportion of the students, or how many of the 1,000 students would be getting C's on the exam, approximately? Now, the mean is 50 points, the standard deviation is 10 points. So this range from 40 points to 60 points, this interval from 40 points to 60 points would be all the scores within 1 standard deviation of the mean. Well, we're asking the question, what proportion of the values are within one standard deviation of the mean? That is, what proportion of the test scores will be between 40 points and 60 points? Chebyshev's theorem doesn't tell us anything. We get no information whatsoever. So if I'm unsure what shape the distribution is taking on, Chebyshev's theorem doesn't tell me anything. But if I assume an approximately normal bell shape for the data, the empirical rule says that about 68% of the test scores, about 680 out of the 1,000 students or their test scores, will be within one standard deviation of the mean. That is between 40 points and 60 points. Now let's say that instead of the interval from 40 points to 60 points, I decide that the C grades are between 30 points and 70 points. So these would be scores within 2 standard deviations of the mean. So what proportion of the test scores are within 2 standard deviations of the mean, between 30 and 70 points? Now, Chebyshev's theorem says something. Chebyshev says at least 3/4 or at least 75% of the test scores, that is at least 750 of the 1,000 students in the class, score between 30 points and 70 points. Now, it could be more. It could, in principle, be 80%, 90%, 99%. It depends on what shape you're talking about. Again, we could be talking about a variety of possible shapes. Bimodal, this U thing, could be a bell. Now, if we do assume an approximate normal bell shape, the empirical rule says that about 95% of the test scores, about 950 out of the 1,000 students have scored between 30 and 70 points on the exam. So it's more of a pinpointing. Remember, Chebyshev's theorem gives us lower bounds. 3/4, 75%, these are lower bounds. It could be more. I'll do this in blue. So Chebyshev's theorem gives us lower bounds. It could be 100%. The empirical rule actually pinpoints an estimate. So finally, let's say that I say that a C is between 20 points and 80 points. Very wide swath there. I think almost everyone should be average. So what proportion of the values are within 3 standard deviations of the mean? That is between 20 points and 80 points. Chebyshev says at least 8/9 or at least 89% of the test scores will be between 20 points and 80 points. It could be everyone though. If I assume an approximate normal bell shape, about 99.7% will score between 20 points and 80 points. So almost everybody, about 997 out of the 1,000 students, basically about everybody, are scoring between 20% and 80% on the exam. So again, the empirical rule actually pinpoints particular estimates, but that assumes normality. That's a really key, important assumption. Chebyshev's theorem applies to a variety of distributions. It's robust or distribution-free, but it only provides lower bounds. And for the score that's within 1 standard deviation, the lower bound is 0%. There's no information whatsoever. Now notice that the results from the empirical rule are consistent with the results from Chebyshev's theorem. So notice that, the 68% is at least 0%, the 95% is at least 75%, and the 99.7% is at least 89%. The empirical rule is consistent with Chebyshev's theorem. It does not violate Chebyshev's theorem. Remember, we assume these if we have a normal bell shape. We don't assume these for these other weird shapes. Now, you might be asking, well, come on now. If I have all 1,000 test scores, if I have an actual census, can't I just look at the 1,000 test scores on the Excel spreadsheet, maybe sort them, and have Excel count how many scores are between this score and that score? That's true, but let me pose for you the following scenario. Let's say that my teaching assistant, Igor, helps me out on the night of the exam. So these 1,000 students are taking the exam. and none of them cry and go running out. All 1,000 students turn in their exams. Now, after all the exams are turned in, I may ask Igor, so Igor, I'd like to get some estimates going. So why don't you randomly select, say, 7 exams, grade them in the next hour, and report to me what your sample results are. And then based on that, we'll try to estimate what's going on with the class overall. So let's say that Igor takes the 1,000 exams, throws them up in the air, I duck, and Igor randomly grabs 7 exams. He finds that the sample mean is 50 points. And we assume that the sample mean will ultimately reflect the population mean. We'll talk about the inference component later in the course. And let's say that Igor finds that the sample standard deviation S turns out to be 10 points. So again, S is the sample standard deviation. We just have sample data, so we can't get the population mean or population standard deviation yet. So based on the sample, Igor gets from the sample of 7 tests a sample mean, let's say the sample mean is 50 points, and a sample standard deviation. Let's say the sample standard deviation is 10 points. Well, then based on the sample data, based on the sample statistics, I can use Chebyshev's theorem and the empirical rule. So let's say that I decide that a C grade will be something between 30 points and 70 points, basically scores within 2 standard deviations of the mean. Then right off the bat, I can say that by Chebyshev's theorem, I can estimate that at least 750 out of the 1,000 students should be getting between 30 points and 70 points, a C on the exam. I'm assuming that X bar and S will do a good enough job of estimating mu and sigma. But basically, by Chebyshev's theorem, I would estimate that at least 75% or at least 750 of the students will be getting Cs. If I further assume that the test scores will follow a roughly normal bell shape, I can say that about 95%, about 950 of the 1,000 students will be getting Cs in the class. We may be getting a lot of disappointed pre-meds, by the way, if that many students are getting Cs on the test. Perhaps it's been the case that in previous semesters, I've seen bell-shaped distributions, so I might feel comfortable in assuming that for now. Or I might just assume that we're going to get a bell shape, and it's just that I want a more precise estimate. I'll go ahead and take this assumption so that I can get this more precise estimate. If I'm not willing to bet on what the shape of the distribution is, I'm stuck with Chebyshev's theorem. So based on the sample statistics I get from Igor, I can make predictions about how many Cs I'm going to get in the class. By the way, an issue that I could have addressed at the beginning, why are we looking at these particular scores? Well, again, 50 points is the mean. If the standard deviation is 10 points, 60 points is 1 standard deviation above the mean, mu plus 1 sigma. 70 points is 2 standard deviations above the mean, mu plus 2 sigma. By the way, 80 points is 3 standard deviations above the mean, mu plus 3 sigma. 40 points is 1 standard deviation below the mean, mu minus 1 sigma. 30 points is 2 standard deviations below the mean, mu minus 2 sigma. And 20 points is 3 standard deviations below the mean, mu minus 3 sigma. Next up, what would be an interval of usual or typical values? And what kinds of scores would be unusual? Next time.
So what's an unusual score? We'll do that next time. Any questions so far? Any questions so far? Chebyshev. All right. All right. Anyway, let's go on. Oh, wait. Actually, before we go on, you know what? I want you to meet my assistant Igor. Let's do that.